Well, what we've been doing in the last lecture was to look at how when atoms combine together, we get molecular orbitals, and the theory that was used was the linear combination of atomic orbitals to form molecular orbitals. And we considered that for, say, 2 hydrogen atoms or 2 helium atoms. Right? That was what we ended with. Well, we can extend this idea to a larger collection of atoms and develop what will be known as the band theory of solids. We begin by looking at 3 hydrogen atoms. We know the picture when we had 2 hydrogen atoms. As they were far apart, they had their 1s orbitals. When they came closer together, one formed a bonding orbital and an anti-bonding orbital, and then the 2 electrons went into the bonding orbital, thereby producing the hydrogen molecule. What happens when we bring, by analogy, 3 hydrogen atoms together from infinitely far apart? As long as they are far apart, they again have their individual 1s orbitals, atomic orbitals. Okay, we'll distinguish constantly between atomic orbitals for isolated atoms and molecular orbitals for a solid or a collection of atoms. So when they're far apart, they each have their orbitals. When we bring them, what do we think will happen? By analogy with the previous examples that we have for hydrogen and helium. What would you think? When you have 2 atoms, we form 2 orbitals. One is symmetric, one is antisymmetric, or bonding and anti-bonding. Now I have got 3 atoms. What do you think will happen?
They will not form a stable configuration.
Well, we'll come to that conclusion eventually. You're right. But that's more a guesswork or something that you know from experience. But in terms of orbitals, what do you think will happen? Will there be an overlap of orbitals as we get closer and closer to form molecular orbitals? If so, how many might form? What would be your guess? Or seems logical, kind of. When I had 2 atoms, I brought them together. The combination of these orbitals ended up with 2 molecular orbitals. I now have 3 hydrogen atoms. I'm still not drawing conclusions about whether they will be stable or not. But all I'm trying to do is what will be the overlap of these 3 atoms, their atomic orbitals look like. So we end up by combining these 3 atomic orbitals to form molecular orbitals, 3 molecular orbitals, which we will name, okay, molecular orbitals are formed. And we will call these psi A, psi B, and psi C. So these are 3 molecular orbitals that are formed from 3 psi 1s states, right? In the atomic state, they were all just 1s orbitals having the same energy. Now I've combined them as we brought them closer and closer together to form 3 molecular orbitals. Now, considering symmetry requirements and various things like that, there are 3 different ways in which we can add the different orbitals, the atomic orbitals. So I've got, for the 3 atoms, I've got psi 1s A, psi 1s B, and psi 1s C. These are the 3 atomic orbitals for the 3 atoms. To create my 3 molecular orbitals, I have different ways of combining these, and there are rules that are determined. We are not going into the great detail. But fundamentally, it turns out that psi A is formed by a simple addition of these 3. Psi 1s A plus psi 1s B plus psi 1s C. Psi B, on the other hand, is formed by subtracting psi 1s A minus psi 1s C. The B orbital is not playing a role in the formation of this particular molecular orbital. And then for psi C, we have psi 1s A minus psi 1s B plus psi 1s C. Okay. These are 3 possible ways that they're allowed to combine in according to various rules that are there for such combinations. So as we sort of guessed just intuitively, 3 molecular orbitals form with these sort of combinations. When we use the term psi1sa, what we are meaning is the orbital that is psi1s centered around atom A and with a radius Ra. That's what we are meaning when we are using the symbol psi1sa. And each of these atomic orbitals, which have got the subscripts 1s, are really exponential. We saw this earlier. Okay, they are related to an exponential of minus Ra, which is the distance from the nucleus of A, and A0, which is the Bohr radius. Can you see that? Maybe I'll hold it up a little. So each of the atomic orbitals that has combined to form these 3 molecular orbitals has got a function that looks something like this in terms of exponentials. We can illustrate these 3 molecular orbitals graphically. I'll try to sketch these as best as I can. The positive sign there shows the nucleus, the positively charged nucleus. And what we have here is that we had wave functions that are exponentially decaying around the symmetrical center. Okay? And so it is the combination of these. So what I'm showing by the dotted lines here are the individual atomic orbitals that have now added up. Remember, for psi1sa, what did we have? It is the addition of these 3 orbitals symmetrically, right? So we have ended up with these 3 combinations here, and the overall result is this solid line that we are drawing as psi1sa. So these represent the nucleus of A, B, and C. Similarly, psi b can be sketched. Now it's psi b was what? It's the difference between A and C. There's no B involved there. So it looks something like this. Okay. This is how they are combining. What I'm showing is simply graphically how the atomic orbitals are combining to give us the molecular orbitals. The 3 nuclei are still there, but in the formation of this particular molecular orbital, the atomic orbital of B is not involved. It's simply a subtraction between the atomic orbital of A and the atomic orbital of C. That's why we are not even showing B in the picture there. Similarly, now for atomic orbital C, what we have is something like this. Again, the dotted lines show the atomic orbitals themselves as they are unperturbed, and after the combination, what it looks like. The solid line shows the combination. This is where we have psi1a minus psi1b plus psi1c. Each of them is the positively charged nucleus, right? I'm showing the locations of the atoms, the nuclei, by those positively charged symbols there. So all these are the 3 that have now been brought into proximity with each other, and now their wave functions are overlapping, right? And when they overlap, there are 3 possible ways in which they are overlapping to produce 3 molecular orbitals. And these are the 3 molecular orbitals that form. In the first case, it's simply an addition of the 3 wave functions, the atomic orbitals, which were the 1s orbitals. In the second case, it's a subtraction of of A and C. And in the third case, it's A minus B plus C. These are the 3. Various rules are there that determine these. But these are 3 that will form. Okay? So now that we know that there are 3 molecular orbitals that are forming, the next question that arises is, what about the energy levels related to these molecular orbitals? Okay? So we want to ask ourselves the question, what will the energy levels look like? And again, by analogy with the previous case, we can make a guess. They're going to be split up in 3 different levels. They'll have 3 different energies, right? In the case of hydrogen, we saw the lower one being my bonding and the upper one being the anti-bonding case. In this case, I have 3 energy levels, EA, EB, and EC, corresponding to the 3 molecular orbitals, psi A, psi B, and psi C. And when we plot an energy versus separation diagram as before, we will get that when they are far apart, we have 3 1s orbitals. Right? Each of them has got its own 1s orbitals. They are all having the same energy, and we are not violating any Pauli's principle or anything. That's not a problem because they are not interacting. So these 3 orbitals can hold up to 6 electrons by pairing. But we have only 3 electrons to worry about in this case because there's only 1 electron in each hydrogen. So as they come closer together, as before, now we'll have 3 different orbitals that are forming. Okay? And the energy levels are given by EA, EB, EC. And each of these molecular orbitals can now hold 2 electrons. So I've got 3 electrons to distribute across this system. And when we look at it, I can do this and this. That's all I need. The minimum distance there being what might be expected if a molecule H3 were to form, the minimum distance, and this is R is equal to infinity. Okay? So these 3 electrons have distributed themselves. Now what we can do is compare what was the situation when we had 2 hydrogen atoms brought together. Where did all the electrons go? Into the lowest state. And in that case, we found that effectively the energy of the molecule is lowered by coming into a molecular bonded form as compared with 2 isolated atoms, because both those electrons went in here. And now my sketch is not very accurate, but in the case of H3, by comparison with H2, what we will find is that the overall energy of this system, because it goes into a higher energy state here, is higher than when we had H2, and in the case of these isolated atoms. So they preferred to go as H2 rather than as H3, which is what you commented early on, right? You said H3 is unstable. That is for this reason that after the orbitals form, when those 3 electrons are distributed into these orbitals, molecular orbitals, the overall energy of that molecule, if it can form, is higher than that of H2. So it doesn't want to stay as H3. It would rather combine as H2 than as H3. Okay? So H3 is unstable as a consequence. Now we can extend this idea even still further with a collection of n atoms. We did with 2 atoms, and now we are bringing 3 atoms. And I'm going to extend this idea to n atoms to form a solid. Okay? So we just take the same idea, extending to n atoms to form a solid. And n is very large, obviously. We'll see that what is the magnitude of this n. Let's consider a specific example, say lithium. Lithium's electronic configuration, 1s2, 2s1. That is, there are 3 electrons to worry about. It has atomic number 3. So I take n lithium atoms that are infinitely far apart. That means they're not interacting. And now I bring them in close proximity to each other. Now by comparison, you look at it. This is a closed shell. Think of hydrogen. And in the next shell, I have 1 lone electron that is orbiting in a s orbital. right? There's place for 2 in there. So it's somewhat like hydrogen in that there is a closed shell around which there is one orbiting electron. And we're not going to worry much about the closed shell, as we will see, and I'll tell you why. Okay? So there is a resemblance between the lithium and the hydrogen that we have considered so far. That's one reason to take up the lithium. It's very similar. The inner shell is all closed. We don't have to worry too much about it. But the outer electrons interact with each other as we bring the electron closer together. Now, when we have n atoms of lithium, how many orbitals do we expect to form? Molecular orbitals do we expect? Seems again, I mean, we had 2 atoms, we formed 2 orbitals. We had 3 atoms, we formed 3 orbitals. When we have n atoms, we expect a combination to give us n molecular orbitals. All right? Now remember, this n here is rather large. And when we talk of a solid, we are talking of what magnitude? Number of atoms per centimeter cube for an average solid. Okay, 22, 23, 29 maybe, depending on the units. If you go to per meter cube, probably you'll end up with 29. But 10 to the power 22 to 10 to the power 23 is the kind of numbers we are talking about. So if that many atoms are involved, we are talking of 10 to the power 22 to 10 to the power 23 orbitals that are formed by the bringing together of these atoms to form a solid. Remember, I said the 1s is not significant. You see, the 1s level electrons are very close to the nucleus. So by the time you have the overlap of 1s electrons, much before that, the 2s, which is further out, has already interacted. And you are bringing them closer and closer together. You're beginning to experience nuclear-nuclear repulsion. And this is a closed shell, mind you. So it has no driving force to interact further. It's satisfied its valency. So by the time you get its interaction, the nuclei must be very close to each other. You've got repulsive effects and all that. Much before that, the 2s shell is going to interact. And it is for that reason that when we consider the formation of lithium solid, we are not worried about the 1s. The splittings and all that of that is not going to happen anywhere near where we will form the 2s orbital splitting. So we'll focus only on the 2s orbitals from now on. All right? It's the combination of the 2s orbitals, n number of 2s orbitals, that we will worry about from now on. So we have n atoms being involved here. How many 2s electrons are there? Since there's only 1 electron per every 2s, so we'll have n number of 2s electrons. And as I said, these are of the order of 10 to the power 22 to 10 to the power 23 per centimeter cube. These are now forming n orbitals, and as we might see, they will be very closely spaced. Okay? Though we draw diagrams that give us these sort of large separations, the actual interaction produces small splitting. So in effect, when we have 10 to the power 22 to 10 to the power 23 orbitals, the spacing between these orbitals, you can imagine, then will be infinitesimally small. They're very narrowly spaced orbitals, 10 to the power 22 to 10 to the power 23 of these. If we write that ET is the energy of highest, of orbital which has highest energy, and EB is the energy of orbital with lowest energy. Effectively, what I said is that ET minus EB is rather small. And given that there are n levels to fit roughly into this 10 to the power 22, then delta E, which is the spacing between their levels, we might say tends to 0. There are very, very small separations between these levels. I'll give you some more numbers. We can do some calculations with this. Okay? So the larger the number of atoms, the more closely spaced will the molecular orbitals be. And so in a solid, we have them very small. Let's draw this graphically. Again, we draw the energy versus separation diagram. And we begin again. In this case, I have a 1s orbital, right, for lithium, far s, the atomic orbitals. It's full. And I've got n such atomic orbitals. Essentially, as we bring them closer and closer together, nothing really is going to happen to them because they're not interacting, except perhaps at very close distances somewhere there, by which point the nuclei are practically touching each other. So for our interest, this has no real significance. On the other hand, the next level, these are the 1s, I got 2s level there. Okay, that's the energy for 1s. And there, how many electrons do I have? 1 electron. And as I bring these together, there's n atoms, and I'm bringing them together, I will have something that looks like this. Pardon the drawing, not very skillful, but you get the idea. There are n levels that are closely spaced. Okay? And there is a minimum, and so when we look at this equilibrium separation, we call that, say, A. The bottom level there is what we earlier labeled as EB, the energy of the lowest energy level. And corresponding to that, we have ET, which is that of the highest energy level. And then these are n levels total that are spaced out here. We also have other levels beyond this, which we will not worry about for now, but we'll come back later. Say E2P. Okay, they're empty because I had only 3 electrons to worry about. And we are not going to worry about that for a second. So essentially, I have an energy level that is related to psi, if we represent each of the molecular orbitals as psi solid n, where n ranges from 1 to n. Right? We have that this is related, this is the energy level related to psi solid 1. This is the energy level related to psi solid n. Okay? And each of these, as we saw earlier in the case of the 3 hydrogens, is a particular combination that satisfies all those symmetry rules and things like that of all the n atomic orbitals that are psi 2s. So there's n orbitals psi 2s. Each of these molecular orbitals is one particular combination of these. It turns out that the lowest energy level, psi solid 1, is simply when we have them all in phase. We just add up psi 2s 1 plus psi 2s 2 and so on to psi 2s n. That means all the wave functions are in phase. We get the lowest energy level here. And correspondingly then, psi solid n is when we have them sort of alternating the wave functions, plus, minus, plus, minus. That gives us the highest energy level. So we labeled that as En, and that one was E1. And the corresponding positions at their minimum was EB, where they are close, the equilibrium separation was EB and ET. Okay? So this is how we have combined orbitals. Everything else, all other combinations result in psi solid n somewhere in between these, n minus 1 and so on. So these are 2 particular combinations that give me the highest level and the lowest level. All other combinations of the 2s atomic orbitals produce levels in between. So because of this fine separation that is there, effectively we can talk, instead of levels, we can talk in terms of a band. Right? energy band, not so much as molecular levels. Effectively, it's like so small, the spacing between them, that we might discuss it in terms of energy band. Remember, at the beginning of the lecture, what I titled this was band theory of solids. What we are developing now is, instead of once it becomes a solid, we are not referring to individual levels there anymore, but to bands of energy levels. Okay, and this band is forming as a result of the interaction of the atomic orbitals. We get these energy bands. And we will call that first band there as the 2s band. Now I've got n electrons, 2s electrons to play with. And if I try to put them in here, what we will see is that I've got n levels. And in each level I can put how many electrons? 2 electrons. So how many levels will get filled up? So n by 2 levels are full. Okay? And the way these are separated, they are not necessarily equally spaced. That's a simplification we are making. So it doesn't mean that it's filled up to half its level, but n by 2 levels are full. Okay, that doesn't mean that the energy here is half that of the whole distance, but there is n by 2 levels that are full and n by 2 levels that are empty. Okay? So when we put in n electrons from the 2s, we get n by 2 full levels, n by 2 empty levels. And this idea that there is a set of full levels immediately connected with a set of empty levels has profound implications for the electronic properties of the material, which we know already. But this is the reason why right from here I've got a space where these electrons can move into very easily. And that's what determines the properties of the material. Now we can look at how I told you just a rough estimate, assuming equal spacing, which is not true, between levels. And knowing that the difference between ET and EB, remember what is ET and EB, is this gap here. Determine, okay, given that ET and EB is, say, roughly of the order of 10 electron volts, you are asked to determine what is the energy separation when they are at equilibrium position. Remember, energy separation between the levels depends on how far apart they are. Right? Because here there is a different spacing between levels, here there is a different spacing, and so on. So the maximum spacing is here, not here. And so the question is related at the minimum or equilibrium separation, what is delta E? We know n is equal to, say, 10 to the power 23 levels. And so roughly what we can say is that delta E is something like this, roughly. What is that? 10 to the power EV. I mean, 10 to the power minus 22 EV. It's practically nothing. And that's why we heard saying it's no point now talking in terms of discrete levels. We're practically talking of continuum. They're so closely spaced that we don't even need to talk about discrete levels anymore. We talk of a continuum of levels that are available where they can easily cross that 10 to the power minus 22 EV if little energy is available. So this will be our description from now on in terms of a band, which is basically a continuum description. I ignored the 2p levels that I had drawn earlier. Right? I said just mentioned that there are 2p levels also and so on. In fact, there's 3s also. And when we look at how these will also interact with this picture here, we can redraw this. If I draw it there, we'll have utter confusion. I get my 1s, 2s. I'm not drawing all those intermediate levels there. You can guess that. And then I got 3s. Oops. 3p. I'm sorry, 2p and 3s. Yeah, you're right. 3s. It's just a schematic. Maybe I'll use a different, well, I don't know if a different colored pen even appears on this graph. But here what we know is that I've got it full up to some point. These are all full of electrons. But what we are seeing here is that even though the 3p and 3s, I'm sorry, 2p, what did I write there? 2p and 3s don't have any electrons to start with, the levels interact all the same. And when they interact, what I'm seeing is that notice how the minima are at different positions. So the outermost orbitals are interacting before you get closer and closer. But what we are seeing is that now I have overlapping between these orbitals. So not only do I have empty states just in the 2s level, I've actually got a whole set of empty states that extend all the way up there. Okay? Practically to the vacuum level where the electron is free to go. Now you may wonder, what about 3D and all that? Well, by the time we get to 3D and all that, the electron is so far out from the metal, it's free. It's outside the metal. So even though there are 3D and all theoretically orbitals that can overlap, we are not even bothered with it because effectively there is no, the electron doesn't even see those things. It's already out of the metal by that point. But this effective overlap of the empty orbitals also means that I end up with having a series of empty states that are overlapping with each other, giving my electrons that are filled up here opportunity to be excited to higher and higher energy levels. Conduction, as we remember, is essentially an exciting to higher energy levels that are available. So we will see later that in some cases we end up with gaps and so on, but in this case they're all overlapping all the way to the upper level. Okay? Just for completion. And we can redraw this in a different way, that there is a series of overlapping levels. Of which the first one is half full. Okay? And we've got one band somewhere here of the 1s, 2s, 2p, 3s, and so on. So by the time you get there, it's practically at the vacuum level, which means energy of the electron to put it's free. It's out of the metal by that point. Okay? In here, it's still within the metal. But once it gets to the vacuum level, it's out of the metal. So further levels we don't even need to worry about. And so what this overlap shows me is that this half full band that we have 2s, the electrons can easily be excited into higher and higher levels till they are removed from the material. Now we can give a name for all these levels and so on, but one of the things to remember is how do we define our energy level when we give values to it? I mean, which is my 0? So there's a couple of different ways we can talk about it. Either I can have 0 at the top, vacuum level, or I can talk in terms of 0 at the bottom. A simple illustration that shows how the energy goes on, the potential energy is going on increasing negatively, that means it's more attraction, is to use the idea of a mine. I just saw this in a book the other day. You see, if you have a mine, an underground mine, and you have a shaft that is going down, and then there are some horizontal shafts where the miners are digging. Okay, I'm just drawing two for simplicity. So this is a mine shaft, and there is a lift here. And there are some miners who are working here, and there are miners working here. And we talk in terms of how much energy does it take to bring them to the surface. Okay, because here we are acting against gravity, which is pulling them down, which is like the nucleus acting on the electrons and sucking them down, close to it. Obviously, we see that the one that is at the level down here, it will take more energy to bring it up to the surface. And by analogy, what we're saying is that what we call the vacuum level is this surface, where they're now free to go home, or whatever, the miners. But here, the level that is here or here, we can say that this has got minus some energy with respect to the surface. We have gone down, and the one that is below it is even deeper. So that's one way of looking at energy levels in terms of how much energy does it take to free the electron from its attractive potential that is given by the nucleus. Another way we can look at it is, so in that case we will define it as 0, and I will say that at the bottom here there is some negative energy. I can define the energy level in a different way. Let me redraw that idea without using minds. We can simply draw it as before with a half full band, and that's my vacuum level where it's essentially free. So my one illustration was where we will call it 0, and let's say in the case of lithium, which we were considering, the bottom here is something like minus 7.2 eV. This level here has a particular name which we call Fermi level. That's the level where we have the highest energy for the electron, and when we specify it at 0K, then we use the term EF0. Okay? So EF0 in this scheme of energy descriptions has got a value for lithium of something like minus 2.5 eV. We can do something else. I can call this 0. I mean, it's sort of arbitrary what I call 0, right? And so by in correspondence with this being called 0 eV, then my Fermi level sits at plus 4.7 eV, which is the difference between these two. And then the surface here, where it's free, is then 7.2 eV. So it's a matter of definition that we agree upon which level we are using as our reference level. I could either use the vacuum level or I can use the bottom of the band. From now on, for various descriptions in this case, we will use this idea that the bottom of the band is at 0 and energies are being described with respect to the bottom of that band. Okay? It's simply a matter of convention how we describe these. We're choosing the convention that the bottom of the band is 0 electron volts, and then correspondingly in the case of lithium specifically, the vacuum level is
plus 4.7.
It is plus. I didn't write minus. I just drew a line there, so it appears to be. You're right. Okay? So this is one convention that we will use from now on. Okay, there's one other term that we can take, an important one in the case of metals. What is this energy between Fermi level and vacuum level? It has a specific name. We use the symbol phi, and phi is called the work function of the metal. Phi finds a lot of use in a number of different cases, including in semiconductor metal junctions and so on. It is called the work function of the metal. That is the minimum energy that is required to get an electron out of the metal and free it. So everywhere here the the electron is still bound, it is free to move, but it is still somewhat attached to the nucleus. It can move around within the metal, but once it crosses this vacuum level, it's out. And so phi, my work function, is what is defining the minimum energy level that is required. To hold on to this diagram for a second, at T is equal to 0K, what's the probability of finding an electron down here, below EF, EF naught? 1. Some of you are getting ahead of your... Yes, we'll see that what is Fermi level defined later on. But the probability of finding an electron below EF at T is equal to 0 is 1. All the electrons are below that, so you will expect to find it there. And correspondingly, the probability of finding it above EF naught is then 0. Okay, all the electrons are below this at T is equal to 0. At some finite temperature, because it will get energy, we will excite to these empty levels that are available. But at T is equal to 0, there is nothing there. When we excite electrons at T greater than 0K, the excited electrons that are there in these empty states form what is called an electron gas. The term electron gas is used because, sort of like gas molecules, they're free to wander around. They're still within the metal, but they're not attached to any particular nucleus. In fact, we can no longer identify any particular electron with a particular atom. So once they're in this level here, it's just a sea of electrons. That's the other description of metallic bond, if you remember from earlier lecture. That is a sea of electrons. There's a continuum of electrons, and so the electrons behave sort of like a gas. They're free to just move around in those levels. Now the description that we have is no longer that of a stationary wave description. The wave function is described as a traveling wave. The electrons just move around. They're not attached to any particular thing, and they can move around. And I gave a wave vector, which we saw earlier when we were discussing quantum mechanics, k for the electron that is now moving around as part of this gas, and correspondingly a momentum, which we know to be h bar k, right? That's basically a restatement of the de Broglie equation. So P is equal. This is what the electron that is moving around as part of the electron gas is described as. Here are a few values just to give you an idea before I go on to something a little different. Phi and Fermi level at 0 Kelvin. Just a quick glance. For silver, the work function is 4.26 eV. Fermi level is 5.5. For aluminum, 4.28. Fermi level 11.7. Copper, 4.657. And for lithium, it's 2.3, 4.7. Now, if I wanted to make something, say the tip of a scanning electron microscope, you know how a scanning electron microscope works, right? You heat up the tip, electrons come out of it, they are focused, accelerated, and you create an image as it interacts with the material. I want to make a scanning electron microscope tip. Which material would you choose? Why? Very good. See, that work function has some practical implications. How much energy does it take for me to liberate electrons out of it? And I could do that by heating, and we'll see some other examples later also. So here is, by using the information of knowing how the band is in these materials, we can use it in a practical sense. Not that lithium is actually used for an SEM, but just among the list of materials that we have chosen. Actually things, more exotic things like lanthanum hexaboride and all are used. Tungsten is also a good one for that case, by heating that, because you can heat it to a very high temperature. The problem with lithium is by the time you get to a high enough temperature, you've probably lost your lithium, right? That's the other practical side. I just, based on, this is how your questions could be. You know, when you think of real questions in your exams and things like that, there are many considerations, but you may not have all the information. But based on what you know that is given to you, as he hazarded a guess, that lithium is a probable candidate in this case. Okay? Let's look briefly at the properties of these electrons within the band. Just recalling, all states up to EF0 are full. Secondly, electrons are essentially free in the form of a gas. They are available there. Okay? So the potential energy term, how are they bound to something, is obviously then what? For such electrons, how would we describe the potential energy term?
0.
Very good. They're not bound to anything, so what do we talk of for potential energy? So that means potential energy is roughly, or for all practical purposes, 0. Which implies then that the total energy E is nothing but the kinetic energy. There's no potential energy term, so it's nothing but the kinetic energy of these crystals. Now you can describe the kinetic energy in different ways. Obviously one of the ways is half kinetic energy is half mv squared. Now I also know, to write this in terms of my momentum, I know that P is equal to mv. Right? Momentum is equal to mass times velocity. And substituting then for V in this equation, I end up with kinetic energy is equal to P squared by 2m. And we just saw that the total energy of these free electrons is nothing but their kinetic energy. So I can write that it is equal to E. Now I can make a sketch of E versus P. The energy versus momentum diagram. Very, very important thing in understanding materials. We'll use this time and time again. Now given that E is equal to P squared by 2m, what would you say about the nature of this curve?
Parabolic.
It's parabolic. My parabolas might look like squares and circles, but I'll say it's parabola so that you'll at least know what I'm drawing. That's P squared by 2m. Okay? And we've got some P average. I'll tell you why it's called P average. And there is a level in energy, which is my EF naught, to which everything is full. So I've got electrons all over this place. It can occupy any of these momentum values and the corresponding energy values. There's no problem because it's full up to that point. Up to EF naught it's full. Okay? So energy is going on increasing with momentum up to EF naught. The point to note is that the electron could move either to the right or to the left. All right, I'll just make one clarification. We are talking of for some hypothetical one-dimensional crystal. This gets modified in 2-3 dimensions, but just simply for a one-dimensional crystal is what we are talking about. Otherwise, you've got px, py, pz, and so on. The electrons could move either this way or this way. So I've got positive momentum and I've got negative momentum. We're defining obviously with respect to some coordinates. Okay? Minus x plus x. What we have to note here is that for every electron at a given momentum value that is moving to the right, there is an electron with the same momentum and same energy moving to the left, because it's all full. And what that implies is that there is no net current. There is electron motion, so we would expect current. But on an average, for every electron that is moving in this direction, there is one that is moving in this direction. So in this case, there is no net current. And so I have an average momentum which is 0. All right? Now what happens when we apply an electric field? I don't know if I'll have time to go through it all, but I'll try to give it to us as briefly as possible and yet clearly. I'm applying a field in this direction, negative Ex. Okay? What happens to the electron? All right, before that, let me put the electron that is sitting here, I call it in position A, and the electron that is sitting here, I call it position B. What happens to the electron that is at A? It's going to experience a force that is given by, and so it will be accelerated in this direction to a position A dash. Right? There is a gain in momentum and there is a gain, a small change in energy. This was my original EF naught. It is able to move up there simply because there are available states. Correspondingly now, the electron that was moving in this direction experiences a force that brings it down to B dash from B, because it experiences the opposite force. So here the electron is accelerated further, gaining momentum and so on. Here there is a deceleration, it is losing momentum and losing in energy. The overall now, the picture is that we've got filled states all the way here, and what I'll say is simply that the average momentum has now been shifted to the right. So for this system, the average momentum, P average, is greater than 0. Okay? And then this corresponds then to a net electron movement in one direction. Everything below this level now has got corresponding electrons moving in either direction, but all the electrons above this are moving in some net direction. So this translates to current flow in which direction? Along this side. Electrons moving that way means current flowing in this way. So because of this change in their average momentum, and as you can see, everything is now below this is cancelling each other, but above it is moving in some net direction. We have an average momentum that is greater than 0, and so we get current flow in direction of the field, which is minus Ex. Okay? Essentially, this change that I've shown seems to be very exaggerated, but the delta change that we have, you know, the energy change, this whole thing here, is rather small. That delta E is of the order of 10 to the power minus 6 eV. So though it looks like a big change, really it's very small. And remember that for many metals, it's something like 1 to 10 eV. All right? So basically what we'll close is by saying that conduction that is taking place here is limited to electrons that are at the Fermi level. The drift of electrons, because it's essentially 10 to the power minus 6 change, mostly the electrons that are sitting at the Fermi level are drifting in one direction in response to the applied field, producing conduction. I'll close with that. We'll probably continue a little bit more on this the next time we meet.